Today we will be talking about the shell elements and see how we can formulate them. But before going into the 2D elements, let's take a look at what we were doing in 1D elements. Remember that when we have a member and we said that we will examine only the axial deformation, we were calling it a truss element. And then we examine the bending deformation, and we obtain the stiffness matrix of a beam element. So in order to perform an actual 3D dimensional analysis by using these 1D elements, we combine these two actions, axial deformations plus the beams for bending deformation, we end up with a frame element. The frame element has 6 degrees of freedom, and we determine the stiffness matrix of this frame element in its local coordinate system. And then, by using a 3D transformation, we can just calculate the stiffness coefficients for a frame element in any directions. Right, we do coordinate transformation. That was our approach in the one-dimensional elements. Of course, in all, our main assumption to do that is these elements are straight elements, so they are all straight. They are not curved, right? If they were curved, then we'll have a coupling between the bending deformations and the axial deformation, and this kind of approach was not possible. Now the shell elements, we can classify them according to their geometry as follows. We can have flat elements, so on the other hand we can have warped or curved elements. Now the main difference between the flats and the warp elements is we can uncouple the stretching action or the axial transformation as here and the bending action in the flat elements. Okay, so let's put that as a note. So in a flat shell element, the stretching and bending effects are uncoupled. So the way we define the flat elements is as follows. So all the points within the element lie on the same plane. If that's the case, we can uncouple the stretching and bending action as we did in the frame elements. Of course, as expected in the warped and curved elements, they are not uncoupled. So stretching and bending are coupled. So let's draw some examples. So let's give an example to the warp geometry. So these 3 points Let's say that they are on the same plane. But its fourth node is on a different plane. So the geometry of the element may look like that. That's a warped element. And we can also have a curved element. Of course, as we can guess, in the warped element, not all the points of this element lie on the same plane, right? One of the nodes lie on the different plane, and of course, when you look at different nodes, we cannot just define a single node that covers all the points in that element, and we have the same issue here. And the main difference of these elements, when you apply an axial load to the node, it will create moments. So in other words, the stretching and bending are coupled, so we have to formulate these type of elements in a different manner. So as a starting point, let's take a look at the flat shell elements. And our approach is very obvious actually. We will do the same thing. We will combine the membrane elements with the plate bending elements, and then we obtain a shell element. And this shell element stiffness coefficients are all defined in the shell's local axis, and now we have to discuss the coordinate transformation, how we can perform a coordinate transformation for a shell element, for a flat shell element. So let's take a look at the flat shells now. For linear analysis. So we will do the same thing. Now we can have a formulation for the membrane action, where we have only these degrees of freedoms, ux, uy, and you can define a drilling rotation. It could be a real rotation or a spurious drilling rotation. You can add a small stiffness to these degrees of freedoms, like we did to stabilize the membrane element. So we have a membrane action, a membrane formulation, plus you have a stiffness matrix for the plate bending action. It could be a thin plate or a thick plate. It depends on what formulation we want to use. We have the plate bending action. So the degrees of freedoms are, let's show this one also, theta x, theta y, and the translation in the z direction. Of course, when you add the stiffness, you end up with the stiffness matrix of a shell element, a flat shell element. And this element will have 3 translational degrees of freedoms, and 3 rotational degrees of freedoms. And basically it will have 6 degrees of freedom per node. And the usual way of numbering these degrees of freedoms are as follows. So ux will be the first degrees of freedom, second, third, fourth, fifth, and sixth degrees of freedom. So we'll end up with a shell matrix, stiffness matrix. It will be a 24 by 24 matrix, and that will be equal to, you have the stiffness matrix for the membrane element, it will be a 12 by 12. And then you have the stiffness matrix for the plate bending element, again it will be a 12 by 12. And since this is a flat shell elements, the membrane action and the plate bending actions are uncoupled, so we have zeros here. Let's show the degrees of freedoms here. Ux, Uy, theta z of the ith node. We have the Uz, theta x and theta y of the ith node. And then you will just shuffle your stiffness coefficients and order your stiffness coefficients as described here. Now for Kp, if you use Kirchhoff theory, you end up with a thin shell element. And if you use the Reissner-Midner theory, you will have a thick shell element. And of course, this is the stiffness matrix in shell elements local coordinate system. So we have to combine, in order to combine the stiffness matrix with the stiffness matrix of other members, we should be able to perform a coordinate transformation. Now let's see how we can do coordinate transformation in 3D for quadrilateral shell elements. Coordinate transformation for quadrilateral shell elements. So let's say that we have a shell element in 3D space. It will be a flat shell element. And in order to do the coordinate transformation, I need a global axis. So let's define our global axis. So let's say that that's x, that's y, and that's z. And in the global axis, let's say that that's what we see. And let's say that this is the first node, second node, third node, and fourth node. Now, the global coordinate system is defined by three unit vectors. We have I, we have J, and we have k. So this defines the global coordinate system. And these are the directions of these unit vectors, I, J, and K. Now I need also three vectors to define the local coordinate system. So we say that we need three unit vectors to define the local coordinate system. Now the question here is, how do we define this? Okay. Now there are actually two approaches for this. Let's take a look at approach 1. Let's take a look at the shell element now in its local axis 1, 2, 3, and 4. So the first step is define vector v12 going from node 1 to node 2. So we know the coordinates of every node. So by using that, we define a vector v12. This vector defines the direction of local 1, or the local 1 direction. And the unit vector that shows that direction can be simply calculated as dividing v12 by its norm. So our shell elements, local 1 direction, will be as follows. So that's the first step. Now the second step, define vector 1, 3 going from node 1 to node 3. So this will be the v13 vector. The third step, the local 3. In other words, the outward unit normal. Direction can be calculated. If I cross product v12 with v13, then it will give me a, with the right hand rule, another vector in this direction, and orthogonal to these two vectors. The cross product of v12 will give me the vector in the outward unit normal direction. I call it v3, and this can be obtained by the cross product of v12 to v13. And the third direction vector can be simply the v3 divided by the norm of V3. So with this step, I determine the third direction. This will be the outward unit normal, U2, U3, I'm sorry. Let's correct that. That's U3. And then the local two direction can be simply calculated by so if I take the cross product of U3 and U1, it will give me an orthogonal U2 direction. So basically we can just say that the second local will be equal to U3 cross product U1. Okay, so that's the approach, and this is a very typical approach used for the shell elements. The reason is now we can just guess the direction of U1. It's always from the first node to the second node. And when you model something, you will see the first direction visually, and you can actually determine what you want as your first direction. And this will help you to visualize, to understand this element stresses in a better way. U3 will be always in the outward unit direction, and we'll have U2 as the cross product of it. The disadvantage of this method, it only uses these three coordinates. It doesn't use the coordinates of the fourth element. If it's flat, there's no problem, but if you have some sort of warping in the element, it's not perfectly flat, then this method will not work. So that's why we have the second approach, which uses the coordinates of 4 nodes, and we will be using this approach when we have a warped shell element. And if you want to model the warp geometry by using the flat elements, this is the approach that you will use. So let's put it as a node. So approach 1 works if the shell element if there's warping, this approach won't work. Because it doesn't use the coordinates of the fourth node. Now let's take a look at this second approach. As the name implies, we will be using the coordinates of all the nodes, okay? So let's say that this is our element. One, 2, 3, and 4. Now the first step is as follows. Direction 1, or let's just say local 1, is defined by the direction of a vector going from node 1 to node 3. So this is our V13 vector, and I can calculate u1 as taking the norm of it, dividing it by its norm, sorry. Okay, so I'll just show it right here. So this will be the u1 direction. Now the second step, draw another vector going from node 2 to node 4. So in that case, that will be the other vector. Let's call it V24. And then we can calculate the outward unit normal, or local tree can be determined as V3 is equal to V13 cross V24. And the third local direction will be then equal to V3 divided by its norm. And finally, so let's show that this is the U3 direction. Local 2 will be then equal to the same approach. U2 is equal to U3 cross U1, and that will give us an orthogonal U2 direction. So the reason of using this approach is if there's some sort of non-uniformity, if your element is not exactly flat, then the approach 1 will not work. You have a warp geometry and you have to do some correction for this warping. We will talk about that. So if you want to do the correction for the warping, you have to use the coordinates of all the nodes. And by using that, you can determine your local coordinates as follows. In that case, your origin will be at the middle of the element. The disadvantage of this approach, of course, assume that you want to model a cantilever by using square elements, and when you look at your local coordinate system, they are all 45 degrees angle. So this is something that you don't want to see. You want to see your stresses or your local axis of your members follow the edges of your elements. This is the very usual way. So that's why while showing the stresses, the approach 1 is usually preferred. But for doing the stiffness matrix transformations, this approach is usually used. Okay, now we see how we can determine the local coordinate system for a shell element. Now the question is, okay, how can we obtain the transformation or the rotation matrix? Now let's take a look at that. Now let's draw first the global coordinate system. This is X. This is Y. This is it. These are the global coordinate systems. And we have, let's show it this way, and 3. Sorry, we didn't use and. These are U1, U2, and U3. These are the shells, local coordinate axis. Okay, and I have the I. These are unit vectors also, so let's show it this way. This is I, J, and K. And let's say that U1, the X component, Y component, and Z coordinate component, U2, L2, M2, N2, and U3, L3, M3, and N3. Now, in order to calculate the cosine angle, or the cosine of the angle between two vectors, we use dot product, right? Let's say if I want to calculate the angle, cosine of the angle between I and U1, I just calculate the dot product, and that will be equal to norm of I, norm of U1 multiplied by the cosine of the angle in between, and that's equal to 1, that's equal to 1. Cosine theta will be then equal to I times N1, and since I has the components as equal to 1, 0, 0, it will directly give me L1. Okay? So, repeating this procedure, for each local axis vector, I can obtain the following table. I have x, y, z, the global direction, x prime defined by u1. Let's write it this way. Sorry. X prime, you use u1 to define it. Y prime, we use u2 to define it. And z prime, u3 to define it. And when you look at the angles, so the angle of x prime with the global x will be equal to L1. The angle of u1 with the global y will be M1 and N1. And if you repeat that, we'll get L2, M2, N2, and L3, M3, and 3. Okay, so this is called direction cosines. of two different local axes, and if you write it as a matrix, well, I will call it as R, and my rotation matrix. So this rotation matrix has all the direction cosines, the cosine of the angles between one of the local axes and all three global axes. Then the second row will be the direction cosines of the second local axis with all globals and so on. Okay, so we call this the rotation matrix. Now the question is, okay, now I can calculate the direction cosines between two coordinate axes. How can I use it? Because I'm interested in transforming the displacements or the forces. Okay, so let's draw the same local axis this time. That's x prime. Z prime. Still doesn't look right. So I think it should be better if I draw it this way. Y prime. Okay. Now on these axes I have or let's reverse it. On the global axis I have this displacement U, displacement V, and displacement W. Now I want to calculate the components on this local axis X, so I need to find out the components of each vector in the local X direction and add them up. Okay, and determine U prime. So when you do that, you'll see that this transformation will be equal to U prime, V prime, W prime is nothing but the rotation matrix multiplied by your displacement components in the global directions. So this matrix will be a global to local transformation matrix. So if you want to reverse the direction, you want to do local to global transformation, you have to multiply both sides by the inverse of R. And again, this R is also a unit orthonormal matrix. So the inverse of it will be equal to its transpose. And the local to global transformation can be done as follows. And finally, your real rotation matrix will be a 24 by 24. Let's call this, give it a different name. Or I don't like this, I want to do this. Sorry for this confusion. Let's use small lowercase r for these ones. Yes, lowercase r for that. And our real rotation matrix for the quadrilateral element will be for each force and moment couple, we will have a rotation matrix. These are all 3 by 3. And so on. your rotation matrix will be also equal to 24 by 24, and your stiffness matrix in the global coordinate system will be equal to R transpose times K times R. This is the stiffness matrix in local coordinate system. And that's the stiffness matrix in global coordinate system.